This video will review research done in recent years to test the therapeutic potential of siRNA and where it might find its medical applications. siRNA is a prime candidate to be a new cancer treatment, as cancer cells are ones that have uncontrolled and unregulated gene expression. Bovan's research in breast cancer aimed to prevent signal transduction in phosphorylation pathways to prevent metastasis, the spread of cancer. While kinases, which are the targets, are easily druggable by conventional methods, the highly conserved active site of phosphatases, the part that matters, makes it dangerous to target using traditional drugs without compromising and damaging other cellular processes, which is not something we want to do. To do this, he needed to knock down the genes responsible. To find them, he did screens on nearly 1,000 targets to find the ones that were involved specifically in the spreading process, also known as epithelial to mesenchymal transition, or EMT. By monitoring focal adhesions, he could see which cells were more likely to spread. He identified a signaling cascade with 2 targets in it, and using short hairpin modified siRNA, he was able to cause the total prevention of both molecular and morphological changes that normally occur when breast cancer cells spread. The results were that this led to an overall repression of breast cancer cell migration, and they no longer invaded other cells. siRNA has also found itself a use to combat age-related macular degeneration, also called AMD, which is the primary cause for vision loss in the West. AMD has stages, with the final stage obviously being full vision loss. Inhibiting a growth factor known as VEGF has become a promising treatment, and it has 2 receptor targets that siRNA could act on. Its inhibition by siRNA could allow us to cure AMD for an extended duration, potentially permanently in a patient, in a way we couldn't do so before. Kaiser et al. Experimented on 26 elderly people who had choroidal neovascularization, which is the disease that occurs right before AMD. The siRNA was injected intravenously to the eye, which I'm sure is the worst nightmare for most people, and the patients were monitored for 84 days. Thankfully, there were no side effects of this, but there was mild discomfort. 9 out of 26 showed clinically significant improvements by moving down a category in AMD, and the rest showed only minor or no improvements. They noticed that the dose didn't seem to affect the impact of siRNA, and this research shows that in the future, if the treatment is perfected, we may be able to use siRNA to play a real role in curing vision loss. In 2018, a company called Alnylam gained approval for a drug called partisiran that contains an siRNA-based treatment for an illness called HATTR that causes an amyloid protein buildup in organs and tissues. The drug knocks down the TTR gene and thus presents the symptoms of the disease and potentially can even reverse it. This treatment has been approved in both the EU and the US, and that shows that siRNA has a real promise in the medical world and demonstrates the progress we've made since 1998. While currently siRNA is still riddled with inconsistencies, hopefully research will continue in the next 10 years or so that we may be able to have a new powerful tool for helping people.